much for this opportunity. I'm going to talk about work we recently completed with Matthias Wacker, who works with the STAN team in Columbia University and Sun State in Oxford. So I'm going to first talk a bit about what is statistical probabilistic programming. So I'm going to spend a few minutes just reviewing recent progress we've made in the area and frame the question. So what is it about? It's about doing Bayesian statistics using a precise formalism programming language. Okay, so what we have is we have programs, and the programs describe generative models. They describe processes that generate random data somehow. And what the semantics does is assign a distribution that translates this formal calculus into the actual probabilistic model. Okay, so what does this program contain? It contains continuous types like the real numbers and the non-negative real numbers, extended ones, and it's really about two effects. Okay, it's the two effects that underlie Bayesian statistics. Okay, so the first one is we can sample for a prior distribution. Okay, and here I'm only going to use the normal distribution over the reals with mean mu and standard deviation sigma. And the meaning of such a sample, say you're on 0 with standard deviation 2, would be this flat normal distribution. The second effect, we're using a very primitive, very low-level effect. Doing that is scoring or reweighting a distribution by a factor R. So if R is a non-negative extended real, we can score a distribution by just scaled up by that factor. Okay, and then a model will look like this. Our prior distribution is we have some normally distributed data. Okay, then we observe some data that we see 1.1, 1.2, 2.7 around x, 2x, and 3x with some noise to the measurement. Okay, we're using this scoring to condition our distribution. So that means that parts of these distributions are going to get score 0, so they're going to disappear, and some others would get very high score. And so when we tally up all those sums and products, we're going to get this density function. Okay, so that's the overall problem. Okay, it's the overall setting, and we're using a programming language syntax to describe formally these distributions and defining in tandem, playing around together. We're defining the prior, and we're changing the likelihood function, defining it together to define a posterior distribution. Okay, so already when we look at just this simple programming language, all it has is some sequencing operation and two effects. We already have a foundational challenge, okay, which is because we have this score operation that can give infinite scores, right? Our measures can go quite high up, right? In parts of the program that will go quite high up. But we want our semantics to be still commutative. So if I sample from independent distributions, I should be able to do it in either order. Okay, when we calculate the semantics, that amounts to the Fubini's theorem. Okay, and if you look at when Fubini's theorem holds, well, we know it holds for probability distributions. Okay, when everything sums up to 1, we know it holds for sigma finite distributions. Okay, so that means that if you can chop up the reals into a countable collection of finite probability places, it still holds. But sigma finite distributions are not compositional. That means that if I push probability through, if I forget about some latent random variable, I will not longer be closed on the sigma finite distribution. So it's not a good invariant in our semantics. Okay? If I say programs denote sigma finite distributions, that's not a good invariant property of measures. Okay? And if we go to arbitrary distributions, then Fubini's theorem doesn't hold anymore. Okay? So the first conceptual challenge was to find a invariant that still satisfies Fubini but allows measures of infinite total measure. Okay? Because the reason we want Fubini is because when we want to do things like exact inference, we want to have some process that calculates exactly the distribution, and sometimes that's possible. We really need properties like commutativity to get things close to each other, so then they reduce and we can simplify the process. Yes?
Very basic, but why not just probability distributions? Why do you want this?
Because what you want is to have these continuous conditioning, soft constraints. Okay, and these scores can go, in this example they don't, but you can find, say, probably density functions that go above 1, and if your prior kind of concentrates you around that point, you can sum up to more than 1. Okay, so that was the first challenge, and some realized that you can use as finite distributions, and we're going to talk about those later. So already, even before we start with higher order functions and fancy features, then you kind of want to set up the semantics and prove theory of that you want. Okay, so that's out of the way. Okay, that's the first kind of step there. Now we want to start using more expressive features when we describe our models. For example, we might want to use, or we want to use higher order functions. Right? And so in our model, to describe our probabilistic model, intermediate parts of it might using higher order functions, like this piecewise construct, that takes a random function, takes a process that generates a random function, and then just repeats it in several places. So it chooses breakpoints and then randomly chooses a random function and plots it. Okay, so this is a run of some 100 samples from this distribution. Okay, and the prior that we gave here was a random constant, so it's a piecewise constant function, and this is 100 samples. Okay, and then we can prototype our model and check different kinds of priors. So we can replace random constants with random linear functions, and we get this figure, and we can check which ones fit the data better, and which one is for better predictions, and so forth. Okay? But here's another challenge. Okay, so because we have continuous distributions, then we want something like measure theory. Okay? But measure theory is no good for function spaces, right, because of an all resolved by Hellman, which says that if I look at all the measurable functions from the reals to the reals, I cannot equip it with a sigma algebra with a measurable space structure that makes evaluation an operation, a measurable operation. So that means that my language now can't apply functions, so that's a showstopper. Okay, so I need to do something different. Again, and currently there's 2 lines of work that do it. One of them was presented earlier this year in Popple about measurable cone and stable measurable functions that do it. And another line of work which I'm going to pursue today is using quasi-Borel spaces that we've presented at LIX 2 years ago, last year, sorry. And this talk continues on that line of work. Okay, so that's one kind of expressive feature that you want to have in your language for modeling. The second one, I'm not going to talk too much about this, but I was going to talk about it on tomorrow at 5 o'clock. Okay. Already when you use something like quasi-Borel space as a semantic model, we can validate Bayesian inference algorithms modularly. Okay, so once we have these higher order functions and inductive data types, W types, I can structure my Bayesian inference algorithms in a way that first is very close to the way people describe them. Okay, so if we look at an advanced Bayesian inference algorithm called resample move sequential Monte Carlo, which has 3 parameters: the number of resamples, the number of particles, the number of moves. I'm not going to describe it in a lot of detail right now. Then you can write this code. So first spawns some particles, then resample, then do some Retroflex Hastings steps in advance, and so forth. So this doesn't look too exciting unless you show it to someone who actually implements these things. And so when we showed it to one of my collaborators, Frank Hood, me and Adam, he looked at it and said, let's see what it does. And he looks at it, and he was shocked. He said, it does what it says it does. He's never used to seeing this implementation of the inference algorithm exactly the way he's used to think about it. So higher order functions and inductive data types let you phrase the inference algorithm in the language that you think about it. And if this piece of code looks cryptic, as usual, it's using a monad stack. Okay, so if you draw the monad stack, it makes a lot of sense. You have some spawn, so you have a stack of representations. It's a sequential transformer applied to a trace transformer, applied to a population transformer, applied to a sampling representation. So this is a monad transformer stack with a monad at the top. And then we apply spawn at this level, resample at this level as well, Retroflex Hastings step at this level, and so forth. So if you want to see more, come tomorrow to Adam's talk or talk to us offline. I'm not going to spend more about this, but we can do it. We can first validate the correctness of these inference algorithms compositionally, and also Adam created a library that uses these. So these are actual Haskell code from his library. So this runs. Okay, so that's another conceptual step. And now I'm going to talk about the topic of today, which is recursion. Okay, so recursion comes in two flavors, term recursion and type recursion. Okay, so term recursion, why we want term recursion? For example, when we want to have recursive processes, like a Gaussian random walk. So I have a thunk here, right? And whenever I force the thunk, I generate a new point and then sample another one. Okay, and if you run it for 100 times, you get this nice diagram. Okay, and so that's at the term level. And if you look at the measurable cones, random work, they can already support term recursion. And this talk is about doing type recursion. Okay, so recursive types, algebraic data types, and dynamic types, because you can think about, we can encode dynamic types using recursive types. And in particular, we can look at idealizations of existing languages like Church or Anglican or Web People or Venture that are untyped. Okay, when they're untyped, you need something like recursive types to model them. Okay, and so that's the setting for today. Okay, so when I say recursive types, just to be concrete what I mean, okay, so in our idealized calculus, we're looking at isorecursive types, okay, based on the fixed point calculus. You can look at Marcelo Fiore's thesis, that has a nice presentation of it. I believe it's from Gunter's book. I don't have a copy of it, so there's an oldie in the audience as well. Okay, so what can we do with isorecursive types? For example, we can give a representation of lambda terms. It's not that might not be the best one. We had a long discussion about those earlier today, but this is where you start. Okay, so we have this fixed point operation that ties the knot. We can represent lambda term, and then we have two constructs for playing around with them. This is what the isorecursive rather than equirecursive types comes from. Is we explicitly roll or unroll, we explicitly pattern match on the values to peel off another layer of the recursion. And in fact, it's enough to just look at recursive types. You can encode, at least at higher types, term recursion using type recursion, and the setting is core by value. So we're looking at core by value with probabilistic effects and recursive types. Okay, so that's the setting. Yep.
Why not regular equirecursive types?
Gabriel, do you want to? So there's a lot of understandability. There's some understandability results going. I mean, it's just what is it? Stephen Dolan here. Yeah. Do you want to give a short blurb as to why that's complicated? Not really. It's complicated.
It's complicated.
It's complicated.
Ah.
Okay. But it just at the idealized calculus, it just makes our life easier. Every term has a unique typing derivation, has a unique type, and so forth. So that's it. Just makes it. It doesn't put conceptual problems that are unnecessary here. Of course, when you as you model richer and richer frameworks, you want to include more of those features. Okay. So and now, if we look at the kind of semantics we usually give to such languages, well, so what do we do? So we have our context variables. Okay, so type variable context, just finite list of type variables. Okay, and then the semantics of a judgment is going to be a functor that has n slots, right? Funct for each type variable. But then it's going to be a mixed variance functor. Some of them are going to be used covariantly, some of them are going to be used contravariantly, and it operates between omega CPO and each categories. These are some kind of categories of domains, and the functor itself is continuous, so that we can really do this fixed point construction and solve it using what's called minimum variance. So I'm not going to go into a lot of details. In fact, one of the benefits of this work is that we can do it in a very high level way without going into all the details at this kind of presentation. Okay, so the question is, which category should we use here that lets us support all the features that we want to support? Okay. Now, it turns out it's hard. Okay, and so now, why it's hard? So for quite a long while, no one has had any semantics that support probabilistic power domain, commutativity, probability domain, some kind of domain theory, so it's used for Recursive domain equations, and Hardy functions. Okay, and if you think about it in a particular way, it relates to the Jung-Tix problem that I'm going to describe now. So the Jung-Tix problem has been open for 20-something years now. And I'm not solving it today, but I'm going to tell you what it is and how I sidestep it, or how we sidestep it. So if you look at those four features, okay, if we can support the first three, if we look at what's called continuous domains. If you're a domain theorist, you know there's a kind of domain called continuous domains, and they let you support Fubini's theorem. And if domains are not continuous, we don't know whether Fubini holds or not. Okay. And now when you start adding Howard functions, then that's the realm of the Jung-Tex problem, which is find a subcategory of the continuous domains that's Cartesian closed. Okay. That's the Jung-Tex problem. I'm not solving it. Okay. So how does the usual approach go? You have a domain. The domain has a notion of Scott open subsets. Okay. Once you have Scott open subsets, you can close them under the Borel operations to get sigma algebra. Even more details in a minute. So you get the Borel sets. The Borel sets give you a measurable space structure that lets you talk about distributions. Okay, so the measurable structure comes from the domain structure. Okay, and to get a handle on Fubini, you need the measurable structure to have a particular behavior. In particular, you want the product to be a particular kind of product. But when you're looking at this approach, you're only generating the measurable space structure from an other theoretic structure, from the domain structure. And in the domain structure, you have a particular kind of product. And when you kind of chase this process to get to the measurable space structure, the product you get at the other end is just not the right product to make things come through. Okay, so this is why this is hard, why the Jung-Tex problem is hard. This is exactly how we sidestep it. Okay, in a solution that's very similar to what Pagani and Tassotti with the measurable cones work. Okay, so what we do is we carry around both a domain structure and a quasi-Borel space structure that are separate but compatible. Okay? And using those two pieces of structure, we can define distributions. And we completely sidestep the Jung-Tex problem. And we get adequate unidirectional semantics. Okay, that's the high level. Okay. So what's the contribution here? Okay, so we just completed it. So we have a category of pre-domains of omega CPOs with quasi-Borel space structure called omega QBS. And we have a power domain construction on it that is commutative. Okay? And you can use these two pieces of semantics to interpret a probabilistic language with recursive types and higher order functions that is commutative. In particular, we have a language that is a variation of FTC, we call statistical FTC because it has statistical constructs, or you can interpret an untyped counter calculus as well. Okay? So what I'm going to do is first talk about these omega QBSs, then I'm going to talk about the power domain construction, and I'm going to spend 2 slides just giving you a flavor of how we did domain theory at a high level, and why we can do it at a high level. But before I talk about omega QBSs, we're going to need a bit of measure theory. So just 1 slide for now. Okay? If you don't know any measure theory, just think about real numbers. Okay? Measure theory is all about looking at the real numbers and then generalizing to all cases. Okay, so what's happening in the real numbers? Okay, the Borel sets are inductively given by all the intervals. Okay, and then if you have a Borel set, you can complement it. That's another Borel set. And if you have a countable collection of Borel sets, you can take the union and you get a Borel set. Now repeat. So you get intersections, you get symmetric differences, and so forth. It gets complicated. Okay, that's the Borel sigma algebra. Okay, and a measurable a function from the real to the real is measurable if its inverse image maps Borel sets to Borel sets. Okay. Now, what's the point of this? The point of this is to define measures. Okay, so what is a measure? A measure is a function that assigns to every Borel set a non-negative external real number that is monotone and Scott continuous. So it's a Scott continuous function. Okay, so we know how these work already. We have expertise here that measure theorists might not usually use. For example, that's the canonical example, is the Lebesgue measure. There's only one measure on the real line that assigns each interval its length. Okay, that's called the Lebesgue measure. And you can extend it to higher dimensions. I'm going to use lambda times lambda for that measure. And now, the last piece of structure you need to know is once I have a measurable function from the reals to the reals and a measure on the domain, I can push it forward to a measure on the codomain. It's called the push-forward operation. And if you use AXI or something to see the only thing the type checks, that's the only thing the type checks. So you can recover it later as an exercise. Okay? And then so that's measure theory for the reals. And now measure theory just generalizes to arbitrary spaces. So you just start with a sigma algebra, which is a collection of subsets that's closed under these two operations, and everything else just generalizes. Okay, so that's very basic measure theory. That's enough to carry us through half the talk. Okay, so the main technical contribution is what what is the pre-domain that we're considering. So it's an algebraic structure. It has three components. It has a carrier set, and in the partial order, it's going to be the domain structure, and a collection of random elements. So what's a random element? A random element is a way of mapping a probability from the real line onto our space. Okay, so if in measure theory, right, what we did is we kind of set things up so we can push forward probabilities from our source of probability, from our random seed. Okay? What we're doing with quasi-Borel spaces is just axiomatize what it means to be a way of pushing forward a probability. Okay, we take that as primitive. That's how we choose things around. Okay, so just quickly, so what is an omega CPO? What is the pre-domain that we're looking at? Well, it's a partially ordered set such that whenever I have an increasing omega chain, I have a least upper bound in the set. Okay, that's basic domain theory. Now, what's an omega QBS? So I have a carrier set X together with a collection of random elements that satisfy three axioms. Okay, so the first one is I can always put all the probability on one point. Okay, every constant function is a random element. Any deterministic element is a random element. And if you think about measurable functions from the reals to the reals, they have this property. Every constant function is a measurable function. The second axiom, if I have a random element okay, that goes from the reals into my space, and I do some measurable rearrangement, precomposing it with a measurable function, phi, then I also get a random element. So I can always rearrange the probability in a measurable way. And that also holds for Borel measurable functions. They're closed under composition. Okay, and the final one is, if I have a countable collection of random elements, okay, is alpha n, and then I can partition the real line into a countable collection of Borel sets, then I can paste them together. I can do a countable k-split. Okay, if I'm in this region, I'm using this random element. If I'm in that region, I'm using that random element. Okay? And if you think about measurable functions, they also have this property. Okay, so these are the three quasi-Borel space axioms. Okay, so the data we have is a omega CPO together with a quasi-Borel space structure, and they have a compatibility condition. So if I look at an omega, so having an omega CPO structure on X gives me a pointwise omega CPO structure on MX. Okay, only it might not be closed on the lobs, and this is exactly what we ask. So whenever we have a pointwise omega chain of random elements, if I take the pointwise lob, that's also going to be random elements. So the random elements are closed under taking pointwise lobs of pointwise omega chains, which is a natural condition. Now this looks natural, but also a bit contrived. We have different characterizations of this condition, of this category of pre-domains, but I don't want to turn hope into legs right now, so I can tell you later what these characterizations are. Okay, but they're very natural as well. Okay, so to get a category, we need to have a notion of a morphism. So what's a morphism from X to Y? Well, it's a function from X to Y that's both Scott continuous on the domain side and a quasi-Borel space morphism on the quasi-Borel space side. So what does that mean? That means that if I have a random element, and I post-compose it with F, I get another random element. So it's an algebraic condition. Okay, so that's our category of predomains. Okay, it's a bit abstract. Let's look at some examples. Okay, so this one example is if I have a measurable space structure, if you still haven't groked measurable space, I just think the reals. Okay, then I can consider it as a quasi-Borel space structure by saying the random elements are the measurable functions. Okay, and I can consider an omega CPO as a discrete omega CPO, just equality. That gives me an omega QBS. Okay, that's a simple example. Let's look at another example. If I have an omega CPO, okay, what I can do is I can take the lobs of step functions. Okay, and that also gives me an omega QBS. And in fact, if I look at the non-negative real lines, external real lines, with the natural order, so the linear order, 0 is less than 1, less than 2, everything in between, and I do this operation, what I get is all the measurable functions, because every measurable function can be approximated by lobs, by countable lobs of step functions. That's one of the definitions of a measurable function. Okay, so I also get this natural omega QBS floating around, and I'm going to be using it in the semantics, right? So I'm going to be using this space, the discrete reals in the semantics, and we're going to be using this naturally ordered real in the semantics. We're going to get there. That's another example. And the last example is this lifting operation. If I have an omega QBS, I can always add a bottom element that's less than everything else, And that bottom element, the singleton, is going to be measurable. Okay, so I'm going to allow the singleton to be measurable. What does that mean? That means that the random elements are exactly those that take a Borel set to undefined, to the bottom element, and then another Borel set to the rest somehow by a random element. Again, natural kind of construction to include. Okay, so that's omega QBS. That's the category we'll be working with. Let's look at its categorical structure. Okay, so what do the products look like? Well, they look quite natural. So if I have two omega QBS's, the product is a Cartesian product, so it's a product space. And the order is the omega CPO product, so component-wise product, component-wise order. And what are the random elements? They're correlated random elements. Okay, so random element, the function from the reals to x, 1 times x2, is a pair of random elements that are correlated together. Okay, in fact, more generally, sorry for the abstract, if I have an omega QBS, I can forget the QBS structure and just get an omega CPO. I can forget and just get an omega, just get a QBS. This functor creates limits, and because these two categories have all limits, then omega QBS also has all limits. So if you think categorically, then it's a very nice place to work in your products. You have refinement types, okay, so you can impose invariants on your data structure. It's a very nice place to work. Okay. What do function spaces look like? So one of the motivations we wanted was to look at function spaces. So, well, the carrier of the function space from x to y is all the quasi-Borel space morphisms from x to y. That's what you want to have, right? That's as good as it gets. And the order is the pointwise order. Okay, as good as it gets. And well, the random elements, well, if you think about it, what they have to be is all the carried random elements, or all the carried morphisms from r times x to y. And that's what you put. You put that, you check it, the exponential, and it is. Okay, so it's a very nice, concrete description of the exponentials. Okay, and then when you're calculating the semantics, you will be using the fact that it's just a collection of functions. So whenever you want to compare two functions, you're going to be evaluating them on every element and use extensionality and so forth. Okay, so that's the omega quasi-Borel spaces category. Now let's look at the probabilistic power domain. And I'm going to need to add a bit more measure theory. Okay? So if earlier we did like measure theory 101, now we're actually starting to think like measure theorists and statisticians. Okay, so first thing we need to know is about S-finite measures. Okay, so what's an S-finite measure? So a measure mu is bounded if the total measure, the measure of the whole real line or the whole space, is finite. An S-finite measure is one that you can decompose as a countable sum of bounded measures. It's a natural definition. Okay? And now comes one of the first fundamental theorems of statistics, which is this. Whenever I have an S-finite measure, I can in fact replace it by the Lebesgue measure on the reals together with a way of pushing it forward onto my space. Okay, so every measure that's S-finite can be presented as the Lebesgue measure on the reals pushed forward onto the lifted reals, maybe peeling off some of the infinite probability that the Lebesgue measure has. Okay, so if my total measure is 1, then I take everything but measure 1, throw that to the undefined part, and everything else goes into my space in the right way. Okay, that's the randomization theorem. And the second principle is what's called the transfer principle. So what does that mean? Well, it means that there is a measurable function from the reals to reals times the reals that lets me split the Lebesgue measure into two Lebesgue measures. Ooh. Very nice, thanks. And together that means that if I kind of use that former random seed, actually I can reparameterize and have a new seed that's independent from what I've used so far. Okay. So, what's nice about omega QBSs is that let us express this internally in the category. Okay, so here we had to kind of talk about functions, right, at the meta level, but here we can actually talk about randomization as a space, the space of all those randomizations, that all the randomizations form the quasi-Borel space. Okay, so what's a randomization? Well, it's a function from the reals to lifted x. That's exactly what we wanted to have. And it actually has a monad structure. Okay, what does it look like? If I have some x, okay, return x, there's an x in there, is the random element that puts measure 1 on x, and then everything else is undefined, peel off the rest of the probability. And if I want to do the monadic bind, what I do is I take my seed, I peel off one copy of the Lebesgue use that to calculate the probability and then sequence later. And what's nice about this, well, what's interesting about this interface is that it looks like a monad, but it's not a monad. Actually, I don't know whether there is any kind of way to choose a transfer function that gives you a monad. Okay, so it's not a monad. Okay. Second component we need.
So it still commutes, right? It's just the monad.
No. So the types work out, but the monad laws don't hold. Okay, if you go one side of the equation and the other, you get different results.
Is there any reason why you can't just feed the seed through using a state monad and therefore recover associativity?
So when you're using a state monad, using a particular kind of flow,
Yeah.
right, if you want to rearrange it, you're not going to get commutativity or anything like that. So that's going to be a different monad.
Right, so then it wouldn't be commutative.
It won't be commutative, exactly. Yeah. Okay. This one is also not commutative. Okay. So the second component to construct a power domain, okay, is Lebesgue integration. So if I have one of those randomizations, and then a function from x to the extended non-negative reals with a linear order, okay, so I can integrate f with respect to that measure. Okay, so how do I do it? If I have alpha and f, precomposing f with alpha gives me a random element of the extended reals, and again that's a measure of functions from the reals to the extended reals, so I can just integrate it using the usual Lebesgue integral. Okay, so I have an integration operation that goes from the randomization monad structure to our continuation monad. Okay, so this is a monad, but this is not a monad. Okay, so what we kind of want to do is carve out, right, the randomized part of the continuation monad. And that's what we're doing with this construction. What we want to do is take this Lebesgue integral operation and carve out all the measures that come from randomizations. Okay, so we need to define how to do this process, this factorization, and well, so this is the construction that works, okay, and we've tried quite a few, but in the next slide I'm going to give you some more abstract reasons of why it works, and if you look at other ways to factorize into an image, they just fail in one of the conditions we'll see in the next slide. Okay, so let's just first understand what's happening here. I have a function from between two omega quasi-Borel spaces, x and 1, and I can factorize it into, well, the image of f, okay, but then I need to get some omega CBO structure. So I'm taking the omega CBO structure from y, so f of x is a subspace of 1, but it might not be closed under lubs. After closing under lubs, I'll start adding lubs and lubs and lubs and lubs and lubs and lubs, and so forth. Eventually it stabilizes. This is how I met Adam. He got it wrong in his undergraduate degree. And so that's where you get the partial order from. And then you do the same thing for random elements. You take soups of point-wise soups and point-wise soups or point-wise soups and so forth until you stabilize. And that gives you a factorization. In fact, it's a factorization system. Okay? So it's on the mono side, it's the full monos, which is a natural kind of class of monos to take. And on the left side, you get what we call densely ebbing. These are exactly the ones where both the elements and the random elements come from the left, closed up, and all it comes from the right. Okay, and it has these three properties that are crucial. So the densely strong epis are closed-handed products, lifting, and exponentiation by the random elements. So it's not closed-handed exponentiation by other things, just by random elements, okay, but by the reals. And if you have these three conditions, you can do some abstract nonsense, and you get this is a monad. Okay, so you can calculate that this factorization is a monad by checking lots of equations, or you can do it abstractly using our paper in Newlands. Okay, so you just do it once and you just check these conditions. It's a nice shot. Yeah, the way you think about it is we take the image of all the randomizations. Okay, and this one has very nice properties, right? It's locally continuous, so we can evolve it in case of joint equations. It's commutative, and it's let us do synthetic measure theory. So that's let us do measure theory inside quasi-Borel spaces. I'm not going to say more because I don't have a lot of time. Okay. So to develop the domain theory, okay, so far I've given you, described a category of pre-domains and then a probabilistic power domain on it. And now what we need to now do is go and develop domain theory for it. In fact, Marcelo Fiore did all the hard work in his thesis. What they did is developed a list of axioms for what it means to be a domain theory. And then his setting has a very little structure, so we need 4 things. Okay, and in our case, it's clear what these four things should be. So we have a category of total maps, right, of non-partial functions. That's going to be on a QBS. You need to say what the domain of definition is. So that's going to be a Scott-open subset that is also measurable according to the quasi-world space structure. You need to say what the poset enrichment is. So that's just going to be the point-wise enrichment. And you need to say what the pointed monad is, and that's the power domain construction, which ends up being pointed. Okay? So this is the only structure you have to supply. Then you have to go and check lots of axioms. Okay? So you check these axioms, and then instead of yours, this gives you all these axioms that you really don't want to calculate by hand. Okay?
Are you sure those are all?
Say again?
Are you sure that's a complete list?
No. So what Marcelo did in his thesis is he identified groups of axioms of varying strengths, and if in one setting not a weaker axiom holds, so you only have a weaker one, a different group of axioms might have a stronger axiom holding that and compensate. So it's a very nice thesis, but you really have to go from left to right, chasing things through. But it's fantastic, and it still works. The only thing we had to add was dealing with arbitrary effects. You only have one effect, partiality. We have more effects.
Wow. It's 94, huh?
Yeah, nice thesis. Okay, that's me done. So I've described the two main constructions, quasi-world spaces and probabilistic power domain. They adequately interpret both a typed language with recursive types and untyped language. What I didn't talk about is the operational semantics, but the standard are Borgström, Andy Gordon, and Will Lago, and Marcin Szymczak. And what I didn't talk about is the slick style characterization of QBSs. I can tell you about that offline if you want. And that's it. I'll take questions if I have any time for questions.
Great. Questions?
Yeah?
So, I'm sure you've heard of approximate Bayesian computation.
Mm-hmm.
Is that a framework for doing that?
Yes, yeah. So the slide I mentioned with Adam's work about modular Bayesian inference, that's approximate Bayesian inference. Come tomorrow for the talk. I'll say more about that in more detail.
I didn't get something.
Yes.
In the last slide, you
Fine.
said,
This
well,
one?
we
Or another
always have
one?
a domain theory if all these axioms are good, right?
So
Then
when
you
these
need to
axioms
do
hold,
that already, or
I already did it, yeah,
current work
I did it, it's done.
verify, and it's
This one check out, and then you can use those to prove this.
so you have the domain theory too.
Yeah.
So that's all there.
It's all there. As I said, I recently completed it, so it's under submission in some conference. You can guess which one it is.
Will this be like the theory for probabilistic programming in the future?
Well, so far it works, but let's try to do things with it until we get stuck, and then we'll see whether we need a better theory. That's how science works.
But do you think it's like it covers enough?
So what we haven't done, so we use this to verify for bidding, for example. What we haven't done is go back to, say, what we did with Adam and check a lot of the approximate Bayesian inference algorithms that we've checked for quasi-world spaces. My guess is that it will work because we have synthetic measure theory that I haven't discussed. Okay, and in the proofs that we used to prove the Bayesian inference algorithm implementations, we mostly use synthetic measure theory. So I'm confident it will come through, but you have to check. Okay, but yeah. So one thing I can do right now. Okay, so you ask about things it can do. I don't yet know how to talk about convergence. Okay, so I have some representation of my model, and then I do some Bayesian inference on it. I get another representation of the model. Why is the last one better than the first one? That's completely missing in my story right now, and I don't yet know how to do it. We have some ideas, not done the work. I don't know anyone in our group who's done the work. If you're doing the work, come and talk to me because it's super exciting.
All right. Let's thank Ohad again.